Um, Hello everyone. So in this video, we will talk about confidence intervals and hypothesis testing for two proportions. Okay, so in many applications, we want to test whether proportions of two populations are equal to each other or not. We may have different alternatives, whether the first one is greater than the second, or the first one is smaller than the second, or both of them are not equal to each other. Well, recall when we are when we are testing two samples, we have, for means, we have x1 bar minus x2 bar, okay, x2 bar minus mu1 minus mu2 divided by in the square root of sigma 1 square n1 plus sigma 2 square n2. So just similar to this, I can use this statistic, okay, p1 hat minus p2 hat minus p1 minus p2 divided by, so this is just like, this is the variance of p1 hat, this is the variance of p2 hat. I just sum them up and take the square root of this. So this is approximately standard normal, okay? But so there is a little catch here. So remember, when we are evaluating the z observed, what we assume, remember, we assume that the null hypothesis is true. So if the null hypothesis is true, it says that, well, the proportions are equal to each other. Okay, so there is in fact a single proportion, right? So recall, we just use the standard pool estimate in the case of comparing two means when standard deviations are equal to each other. Hence, we will do the same thing here. And the new z will be p1 hat minus p2 hat minus 0. So this is just coming from the null hypothesis, okay, p1 minus p2, divided by, instead of that whole mass in the previous slide, we just write a single pooled p hat. Okay, so this is p hat times mine minus p hat divided by n, which is the sum of two samples. Okay, so what is p hat here? P hat is the pooled estimate of the combined sample. How? You just sum the number of successes in the first sample, then the successes of the second sample, and divide it by the sum of the total number of samples in the total number of observations in two samples. Okay. Now, let's make an example. I just want to test the coffee loyalty of the students in Özyeğin University and Yıldız Technical University. And I just asked them whether they favor Cafe Nero over Starbucks or not. So 120 of 100 many students in Özyeğin University just favor Cafe Nero. And 240 students out of 500 in Yıldız just favor Cafe Nero. Okay, so do these data suggest that the proportion of Özyeğin students favoring Cafe Nero is higher than the proportion of Yıldız Technical University? So again, do these data suggest that the proportion of students in Özyeğin University favoring Cafe Nero is higher than the proportion of Yıldız Technical University? Okay, so use a 0.01 level of significance. So, well, the null hypothesis is, so P1 is equal to P0 versus P1 is greater than P2. Okay, sorry, H0 is P1 is equal to P2 versus P1 is greater than P2. So this is of Özyeğin University. Okay, so this is the proportion of Yıldız Technical University. Okay, so alpha is 0.01, which means, so this is in fact P1 minus P2 is greater than 0. Hence, since this is a greater than, I'll be able to just use this 2.33. This is 0.01. Okay. So this is what we have here. Okay. This is 2.33. Okay. So P1 hat, that's equal to 120 divided by 200, which is 0.60. Okay? And P2 hat is 0.48. So the key question is, well, it turns out that 0.60 is greater than 0.48. Why are we making a test? Why are we making a hypothesis test? Just think of this a little bit. Just pause the video and think of this. Well, yes, 0.6 is greater than 0.48, but this is what we have. P1 hat is greater than P2 hat, okay? But what we are searching is, by just looking at this ratio, can we say about, can we say this, P1 is greater than P2? So the parameter that we don't know, the parameters that we don't know, do they have a relationship like this? P1 is greater than P2, okay? So the sample proportions, okay, they're obvious, but how about the population parameters? Can we say this? And this is the real question. This is the real question in all hypothesis testing so far. The p hat, the pooled estimate is equal to 0.51, okay? And the z value, if you just plug in the values, it turns out to be 2.90, okay? 2.9 or 2.90 is, just put it there. Well, it's somewhere here, okay? It's very far away. So it turns out that, well, it turns out that we just reject H0, okay? Because your observed Z, so this is the observed, right? This is the observed. So it's very it's a very extreme value. It's in the critical region. Hence, we just reject the H0. Okay, so as you see this. So the conclusion is the proportion of Asian students who favor Cafe Nero is higher than the proportion of students who favor Cafe Nero in Yıldız Technical University. If you just check the p-value, it turns out that the probability that z is greater than 2.9, okay, which is, let me just throw it again here. This is 2.9, okay. The area here is equal to 0.002, which is 0.2%, which is very, very small, okay? Hence, we can safely reject the hypothesis. So the next and the last thing about the proportions is the confidence interval for two proportions, okay? So the confidence interval for two proportions. Well, uh, okay. So let's say P1 denote the proportion of smokers with lung cancer, and P2 is the proportion of non-smokers with lung cancer. Okay? And we want to estimate the difference in between, or just want to make an inference, just find an interval about the difference of two proportions. How? So just like we did before, we need a point estimate, right? Just like P1 hat minus P2 hat. Okay. So, well, as we said before, we can say that P1 hat minus P2 hat is approximately normally distributed, okay, which mean P1 minus P2 and standard deviation P1 1 minus P1 over N1 and plus this one. So remember, in fact, we just wrote this at the beginning of our hypothesis testing procedure, but then we said that when you are making a hypothesis test regarding the equality of the proportions, we just the proportion of two populations just boils down to a single proportion, okay? But now we are making confidence interval, so we are just using both of them as well, okay? So, well, this is approximately standard normal random variable, okay? So P1 hat minus P2 hat minus P1 minus P2 divided by this whole mass. This is a approximate standard normal random variable. Just using this, okay, in where, remember, I just plug in this value to here to find the confidence interval, right? And the confidence interval turns out to be P1 hat minus P2 hat plus minus the alpha over 2 times P1 hat minus 1 minus P1 hat, P2 hat minus 1 minus P2 hat divided by N2, and here it's divided by N1. So remember, in fact, here I don't have P1 hat because here you have P1 and 1 minus P1, but just like the confidence intervals that we did for the single proportion, we don't have the real values. So what we do is we just plug in, the estimates, okay? So then this interval, this confidence interval is an approximate confidence interval for the difference of two populations, okay? Let's make an example of this so that it becomes clear in your head. Well, a change in a manufacturing process of parts is planned. Okay? So samples are taken under both the existing and the planned process to determine if the new process reduces defectives. So what you do is, so you have a current process and there is a proportion of defective, let's say P1, right? And this is the old process. And there is a new process. You want to switch to this new process, which produces P2, let's say, which produces defectives with a proportion of P2, and you assert that you conjecture that P2 is smaller than P1. Okay, so the new procedure has a smaller rate of defectives. So 90 out of 1,500 parts and 80 out of 4,000 parts from existing and new processes are defective. So these are your what? These are your samples from the first and the second processes. Just calculate a 90% confidence interval for the real difference between the proportion of defectives for the two processes. Okay. So just look at here, P1 hat, it's 90 divided by 1,500, it's equal to 0.06. P2 hat is equal to 0.04, okay? So I have the confidence interval here, just plug in the values there, okay? P1 hat minus P2 hat 0.02, P1 hat, it just comes from here, P2 hat comes from here. And after making the necessary algebra, it turns out that, well, the difference between the two proportions is with how many, what was the confidence interval? It was 90%, right? I am 90% confident that the difference between two proportions is between 0.008 and 0.032. What does this mean? This means that, well, I am 90% confident that, right? P1 or P2 is greater than P1, sorry, P2, sorry. Let me just erase this. I am 90% sure that, I am 90% sure that P1, okay, is greater than P2 plus 0.08, right? So this is the new process. This is the old process. So I am 90% sure that P1 is strictly greater than P2. And the difference is at least 0.08. Okay. So I can safely say that, well, the new process just produces less defective when you just compare it with the old one. Okay. So remember, okay. So this one again says that, well, the new process P2 is smaller than, you are 90% sure that it is smaller than P1 with at least an amount of 0.008. Okay. Okay, so we can conclude, let's read this, at 90% confidence level that the Planck process seems to be improving the proportion of the defective parts. Okay.